so let me remind you that we have two functions. Call one of them capital F of P. This is the Laplace transform of another function, little f of t. Notice these two functions are functions of different variables. And this is how they're related. Capital F of p is equal to the integral from 0 to infinity of little f of t e to the minus pt dt. So again, we're integrating over t here, and it's a definite integral, so after we evaluate it at the limits, the result is something that's no longer a function of t, hence no functional dependence on t here, but it is a function of p because of the p dependence in the exponential right here. So just a reminder, this is a lot like the definition of a Fourier transform. The main difference is in a Fourier transform we had an I in the integral as well, in the exponential in the integral, and the limits went from minus infinity to infinity. Okay? And we had perhaps a 1 over the square root of 2 pi up in front. That's not terribly important. The other two differences are the more important ones. So anyway, we worked out one example, I think last time, of a Fourier transform. Or I'm sorry, a Laplace transform, not a Fourier transform. And that was for the function f of t equals 1, which is of course not a function of t at all, but just a constant. And we found that the capital F of p that goes along with it, the Laplace transform, was equal to 1 over p, at least if p is positive, or better yet, if the real part of p is positive, because p could be a complex number. And this entry was L1 in the tables. Okay, the tables in your book are at the end of chapter 8, and they go from pages 469 to 471. And in those tables, there's a list of what the function f of t is, and then the corresponding capital F of p. There are maybe 30 or 40 entries in that table. I'll derive one more for and each of them is labeled as L something, right? L for Laplace transform, L1 through L30 something. I'll work out one more example, which is L2 from the tables. We're obviously not going to work out, though, every entry in the table. You can use these tables as you see fit. You'll see what some of the uses are for them a little bit more as we go on. Just a reminder that when we do our final exam, I will give you these tables, okay, along with the list of the curls and divergences in the various coordinate systems that I gave you for the midterm. I'll give you both that and these tables so that you'll have them available to you on the final exam. Okay, so anyway, our second example, again, this is entry L2 from the table. The function f of t is e to the minus at, where a is some constant. Right, so that's a function of t. So let's work out what its Laplace transform capital F of p is. So using the definition of the Laplace transform, this is going to be the integral from 0 to infinity of e to the minus at, that's our f of t, times e to the minus pt dt. Of course, these exponentials can be combined. Right? When we have two exponentials multiplied together, we add the exponents. So this is e to the minus quantity a plus p times t dt, again from 0 to infinity. And when we integrate this exponential, we get the same exponential back again. And we divide by minus a plus p, right? The coefficient of t in the exponent. Since this was a definite integral, we have to evaluate this at the limits of integration from 0 to infinity. So at the upper limit, when t is infinity, assuming a plus p is positive, then the exponential will be e to the minus infinity, which of course will be 0. And from the lower limit, when t equals 0, this is e to the 0, which is 1. So we get 0 from the lower limit, 0 from the upper limit, 1 from the lower limit, but since it's a lower limit, we subtract the 1, the minus sign on it will cancel with the minus sign up front of the a plus p. So the result will be just 1 over a plus p. Again, if a plus p is positive, or better yet, if the real part of a plus p is positive. Just like with the previous example we did last time, a plus p, just like p in this case, could have been a complex number. It doesn't have to be real. If a plus p is complex, okay, think about a complex number appearing in this exponential here. A complex number, of course, can be written as like a plus ib, right, where a and b are both real. Any complex number can be written that way. And then the exponential could be split up into two parts, one that has a real exponential, e to the minus something times t, some real number times t, and a complex exponential. The complex exponential, of course, could be written in terms of sines and cosines, right? So in a limit where t goes to infinity, the complex exponential part of this would simply oscillate, right? It wouldn't go to any particular limit, it would simply oscillate. So what's important is what the real part of a plus p does when we evaluate it at the limits. So again, if the real part is positive, this will go to 0 at the upper limit. Okay? So anyway, again, this is entry L2 on the table. So if you look in the column under f of t, you'll see e to the minus at, and the column for capital F of p, you'll see 1 over a plus p. So again, I'm not going to work on every other entry in the table, obviously. There are a lot of them. But we can use that as needed, and again, we'll see some of the uses in a few moments. Another important thing is that we can also show that the Laplace transform, which I'll abbreviate as LT, is a linear operator. Okay, and let me define what I mean by that. First, let me introduce some new notation, just for the sake of compactness here. And we'll be using this notation when we talk about Laplace transforms and differential equations also. But let's define, we use this notation right here, L of f of t. This is just shorthand for the Laplace transform of f of t. In other words, L of f of t equals capital F of p. Right? That was the notation we used for the Laplace transform over here, of course, with the capital F of p. Okay, so this is just a shorthand notation, basically, for writing out this equation right here. Sometimes we'll even shorten this up a little bit more and just write L of f equals capital F. The danger in doing that is you may forget that the two functions, little f and big F, are functions of different variables, right? Little f depends on t, capital F depends on p. If you write it out this way, that's more explicit, okay? But if you don't think you'll be confused by that, feel free to use this notation too. So anyway, what do I mean by being a linear operator? I mean that, first of all, the Laplace transform of the sum of two functions. Let's say we have f of t plus g of t. We want the Laplace transform of the sum. Let's write out what that is, right? Using the definition of the Laplace transform right here. So this is the integral from zero, to minus infinity of the thing we're taking the Laplace transform of, namely f of t plus g of t, quantity times e to the minus pt dt. Okay. Well, we could certainly, inside the integrand here, multiply the exponential times these two terms and write those as two separate terms, and then we can break them up into two separate integrals. So this is the integral from 0 to infinity of f of t e to the minus pt dt, plus the integral from 0 to infinity of g of t e to the minus pt dt. And then using the definition of Laplace transforms, this first term is the Laplace transform of f of t, and the second term is the Laplace transform of g of t. So if you wanted to, you could write this as capital F of p plus, I guess the obvious choice of notation would be capital G of p for the Laplace transform of little g of t. Okay, so in any case, the Laplace transform of a sum of two functions is the sum of their Laplace transforms. That's part of what I mean by this being a linear operator. The other part is that if we have the Laplace transform of some constant c times the function f of t, right, where c is some constant, well, again, let's use the definition of the Laplace transform. This is the integral from 0 to infinity of c times f of t, the thing whose Laplace transform we want to take, times e to the minus pt dt. And of course, c being constant could be moved out in front of this integral. And then this is c times the Laplace transform of f of t, again by using the definition of the Laplace transform. So in other words, if we have a constant multiplying the function whose Laplace transform we're taking, we can pull the constant out in front of the Laplace transform. Okay? That's the second piece of what I mean by this being a linear operator. And by combining these two results, 1 and 2, together, we can combine them to write the following kind of thing, that if we have the Laplace transform of c times f of t plus d times g of t, where c and d are both constants, we can first of all split the Laplace transform of a sum up into the sum of the Laplace transforms, and then using item 2 here, the constants c and d could be moved out in front. So this is the same as c times the Laplace transform of f of t plus d times the Laplace transform of g of t. Okay, so this is really the summary of what I mean for it to be a linear operator. Okay? Just one word of caution, though. Based on this result, you might be tempted to guess that if you similarly had a product of two functions, right, f of t times g of t, and you wanted the Laplace transform of that product, you might be tempted to think that this is the product of the Laplace transforms, but it's not. Okay? So this is not the same thing as the Laplace transform of f of t times the Laplace transform of g of t. There is perhaps a somewhat similar relationship that is true, but it's not quite this. We'll see what it is in a moment. Okay, or maybe not a moment, but a little bit later today. Okay, I want to leave the topic of Laplace transforms just for a moment, but we'll be back to it in a moment. To kind of do an aside where we talk about differential equations a little bit, because the next thing we want to do with Laplace transforms is show how they can be used to solve certain types of differential equations. But to do that, we need to know a little bit about what differential equations are and how we categorize them. There are a number of different categories they fall into. So just as an aside, we'll spend a few minutes talking about that. So a differential equation relates some function, let's call it y of x. Right? So y is a function of x, and one or more derivatives of y with respect to x. Okay? Could be a first derivative, could be a second derivative, could be a third derivative, or any orders of derivatives. Okay? That differential equation may also contain other functions either of y or x, or both. So I'll say and or x. So let me just write down a bunch of examples, okay, of differential equations. And you'll see that they all relate this function y and its derivatives and maybe some other functions that depend on y and x. So I'm going to use this notation, the prime notation, right? Y double prime means a second derivative of y with respect to x. So that could be equal to k times y, where k is some constant. In other words, we're asking to find, right? Our goal here in solving our differential equation is we want to find the function y of x that satisfies the relationship that is described by the differential equation. So this says we want to find some function y of x that if we take the second derivative of y with respect to x, it will give us the same function y that we started with, except multiplied by some constant. Here's another differential equation. Right? X times y prime plus y equals cosine of x. Right? So first derivative of y with respect to x multiplied by x itself, add the function y itself, should be equal to cosine x. We want the function y of x that satisfies that. Right? Maybe a simpler differential equation, y prime equals k, where k is some constant. Right? That one you can actually sort of guess the answer to if you think about it. Right? We want a function that a function of x, that if we differentiate with respect to x, we'll get a constant k. Well, how about y equals kx plus c, where c is both c and k are constants. And if you differentiate that with respect to x, the c term won't give you anything. But when you differentiate the kx, you get k. Right? So that would be the solution. Right? Simple ones like that, you might almost be able to sort of guess the solution. But in most cases, obviously, something like this, you can't guess the solution. Another differential equation, y double prime equals sine of y. Right? So like I said, there could be other functions of x and or y. Right? Like there's a sine y appearing here. Similarly, there was a cosine x appearing there. The derivative could be taken to some power. Right? Y prime could be squared. Right? Maybe that's equal to x. That's another differential equation. Or y times y prime times y equals k, where k is some constant. All right, so these are a bunch of examples of differential equations. Now, the bad news for us is that there's no one single technique that works to solve all differential equations. Okay, if there were, it would be easy, and we wouldn't have to have entire courses on differential equations. But there's no one technique that works for them all. There are a whole bunch of different techniques that you can use depending on what type of differential equation you have. Okay, so one of the most important things about differential equations is to be able to categorize them into these various categories that tell you what technique will be useful to solve them. So let's talk a little bit about those categories. First of all, one of the important ways we classify differential equations is the order of the differential equation, or I'll abbreviate that as DE. That's the order of the highest derivative. Alright, so this, for example, would be second order, right? Because there's a second derivative in it. This one would be first order, because there's only a first derivative, y with respect to x. This one is also first order. Right? This one is second order. This one is first order. And this one is first order. And you could have a third order one. I didn't write that on my example list, right? But if you had a third derivative of y with respect to x appearing, then it would be a third order differential equation. Most of the differential equations that arise in physics and engineering applications, not all of them, but most of them are either first order or second order. Okay? So that's what we'll be concentrating on, both in our discussion today and also when we talk about differential equations at the beginning of Physics 473. Yeah?
So what's the difference between first order and second order?
First order has only a first derivative in it.
Okay,
Second order has a second derivative in it.
Okay.
Right? Y double prime. It's a second derivative of y with respect to x. That makes it second order. This one only has a y prime, not a y double prime. So it's first order. Okay, so that's one important way of categorizing them, right, is to specify the order. A lot of important differential equations in physics and engineering applications are also linear differential equations. So what we mean by a linear differential equation is one that has the following form. A naught times y plus a1 times y prime plus a2 times y double prime plus a3 times y triple prime. Right, depending on what order it is, we may have more terms and so forth. But finally, this is all equal to b. Where the a's, right, the a naught, a1, a2, etc., and b are either constants or functions of x. But the point is they're not functions of y. Okay? So in other words, each term that involves y or a derivative of y with respect to x whatever the y or the derivative of y is that's appearing is always just to the first power. Okay? Right? I haven't allowed in this form right here y to be taken to any power other than 1. Same thing with y prime, same thing with y double prime. Right, so each y, or a derivative of y, no matter what order of derivative it is always to the first power. There is never a term that has, for example, y and y prime multiplied together. There are no functions of y, like sines or cosines or exponentials involving y that appear. Right, the y's and all the derivatives of y are just to the first power. Again, there could be coefficients of them that are functions of x, or perhaps constants, right? But the y dependence is this way for a linear equation. So let's look at the equations I gave you examples of here and see which ones are linear and which ones aren't. Okay? So this one's linear. Right? I could, of course, bring the y. I could, subtract ky from both sides, write it as y double prime minus ky equals 0. That's certainly something of the form there, right? Both y double prime and y are just to the first power, right? There's no y single prime term, but that's fine. The constant in front of, or the coefficient of the y single prime term, the a1 that I called it over there, could be 0, right? That's no problem. So this one's linear. Actually, this one's also linear. Because again, y prime and y are each to the first power. It's okay for the coefficients to be functions of x, and it's okay for the b over here on the right-hand side to be a function of x. Right? That's fine. So that's linear. This one's clearly linear. But these last three are not. Right? These are all nonlinear. This one's nonlinear because it has a sign of y in it. This one's nonlinear because the y prime term is squared. And this one's nonlinear because y prime and y are multiplied together. Right? None of which are allowed in something of the form that we wrote over there. So linear equations and nonlinear equations have different ways of solving them. Usually linear equations are easier to solve. Okay? There's also another way of categorizing, especially within the category of linear equations. A homogeneous equation has the b that I wrote on the right-hand side right here equal to 0. Okay? So, for example, this would be a homogeneous equation, right? Because I could write it in the form y double prime minus ky equals 0. In other words, move all the terms with y and its derivatives to the left-hand side. If what's left on the right-hand side is 0, it's a homogeneous equation. Those are often easier to solve than non-homogeneous equations also. Okay, so again, the techniques depend on the type of differential equation we have.
Are homogeneous equations always linear?
Not necessarily, no. No. You could have maybe something like this. Right? Where I put all the y terms on the left-hand side, the 0 is the right-hand side, so that's what makes it homogeneous, but it's not linear because the y prime term is squared. So not necessarily. Okay? But often, if homogeneous linear equations are going to be, or at least if they're first or second order, are going to be some of the easier ones to solve. Okay. Yeah?
With the second to the last example, if you took the square root of both sides, would it be linear? Where you have y prime squared is equal to x, and just half square root.
Yeah, although it's not exactly the same equation that you had before, because when you take a square root, there could be a plus or a minus sign, right? So you could break it down, I guess, into two linear equations. If you wrote one for the plus square root, one for the minus square root.
Okay.
Is it generally a better idea for solving those, or?
We're not going to worry too much about differential equations like that anyway, right? Like I said earlier, most of the differential equations that occur in physics and engineering applications are either first or second order, and a lot of them, not all of them, but very many of them are linear also. Okay? So we're going to be concentrating on mostly linear equations. Okay? Okay, now, and obviously I can't show you all of the different techniques in the time we have remaining. So again, there will be a lot of techniques for solving various types of differential equations that we talked about at the beginning of 473. But as a general statement, the general solution, and I'll come back and kind of expand on what I mean by that, of a linear, by the way, sometimes people will call these ordinary differential equations. That's what the ODE stands for. And perhaps I should have added the word ordinary over here. Just if you're wondering what that word means, here we talked about y of x as a function of one variable. Y only depends on x, not on something else too. But of course you could have some function of 2 or 3 variables, maybe f of x and y, right? Or f of x, y, and z. And you could imagine a differential equation that involves that function f and various partial derivatives, right, with respect to x or y or z, maybe even mixed partials, right, a second derivative where you take one derivative with respect to x and another with respect to y. So if you have a function of several variables and the derivatives then that appear are partial derivatives, those are called, not surprisingly, partial differential equations. Okay? We will talk about those in 473 also, but it's probably obvious we want to talk about ordinary differential equations first, right? Because they're simpler. So that's what we'll concentrate on now. So again, that's what the ODE here stands for. So the general solution of a linear ordinary differential equation of order n. So again, the nth derivative then is the highest order derivative. The solution has n arbitrary constants. Okay, so what I mean by the general solution is the most general way of writing a function, y of x, that will satisfy the differential equation. Okay? There could be a constant in that solution that could take on any value, and no matter what value it takes on, the function is still a solution to the differential equation. Okay? So if it's an nth order linear ordinary differential equation, there are n arbitrary constants in the solution. So for example, if it's a second order linear ordinary differential equation, there will be 2 arbitrary constants in the solution. Okay? And so the general solution, we know, should contain that many constants. Okay, that's a good thing to keep in mind as we're solving them. Sometimes, however, we want not this general solution, but a particular solution. That not only solves the differential equation, but it also satisfies some boundary conditions. Those boundary conditions are things that specify the numerical values of y or y prime, or perhaps y double prime, or any other order of derivative, depending on what's involved in the differential equation, specifies the numerical values of some of those things at certain values of x. So let me give you an example of what I mean by this. Okay? Okay, so here's our differential equation. Y double prime equals y. Okay? That is a second order linear homogeneous equation. Right? It's second order because the second derivative is the highest order of derivative. It's linear because both y double prime and y are to the first power. And it's homogeneous because I could write it in this form by writing it in the form y minus y double prime equals 0. And since there's a 0 on the right-hand side, then it would be a homogeneous equation. Okay? So we're asking for a function whose second derivative is equal to the function itself. Okay? Well, my claim is that the general solution, and I know you don't know how to solve this yet, so I'm not suggesting that you should know what this solution is, but it's a times e to the x plus b times e to the minus x, where a and b are arbitrary constants. Okay, so this is an example of what we said right here, right? This is a linear ordinary differential equation of second order. So according to what we said right here, the general solution should contain two arbitrary constants, and it does, a and b. Okay? Now, again, at this point, you're just having to take my word for it that this is the solution. But you should always be able to take an alleged solution to a differential equation, plug it back into the differential equation, and show that it is a solution. Okay? That's something that you should be able to do without knowing how to solve them. So for example, right, if I claim that this is the solution, let's just differentiate that with respect to x to get y prime. Right, so the derivative of e to the x with respect to x is just e to the x. The derivative of e to the minus x with respect to x is e to the minus x times a minus sign, right? We bring down a minus sign out in front. So minus b to the minus e to the minus x. And then let's differentiate this one more time with respect to x to get y double prime. So again, the derivative of e to the x is just e to the x. The a comes along for the ride. When I differentiate this term, I get the same exponential back, but I bring a minus sign out in front, which then changes this back to a plus sign again. And notice that that is the same as the expression for y that I began with. Right, so obviously just from looking at it, we can see that y double prime is equal to y, which is what our differential equation said. Right? So in other words, the way you can always do a check like this is calculate, right, take your claimed solution, differentiate it with respect to x however many times you need to get the highest order derivative that appears in your differential equation. Plug everything back into the left side of your differential equation, right? All the y's, the y primes, the y double primes, whatever derivative appears there. And after you combine terms, you may have to do some algebra in a few cases. This time we didn't because it's such a simple equation. But you should be able to see that you get a result equal to the right-hand side of your original differential equation. Okay? So in other words, if you plug in your claimed solution, you should show that you can get an identity out of it. Okay? So this is the general solution. But let's say, just as an example of what I was talking about here, that we want a particular solution to this differential equation. That satisfies, in addition to satisfying the differential equation, some boundary conditions And our boundary conditions are that we want y to be equal to 1 when x is equal to 0. And our second boundary condition is that we want y to be equal to 5/4 when x is equal to the natural log of 2. Okay? It turns out that those two boundary conditions will allow us to determine the values of a and b, right, that meet not only the differential equation, but meet these two conditions as well.
Right.
Okay, and the general rule is however many arbitrary constants we have, that's the number of boundary conditions we need to specify them. Right? Think at this point of, right, if you're trying to solve for a and b, figure out what they are in one particular solution, you can regard them as both as unknowns, and if you have two unknowns you want to determine, you need two equations to do it. So I need two boundary conditions to specify this. Okay? So let's work out the particular solution that meets these boundary conditions. So our first boundary condition says that y is equal to 1 when x is equal to 0. So in other words, in this general solution, I'm going to plug in y equals 1 on the left side, and I'm going to plug in x equals 0 on the right side. So on the right-hand side, that'll be a times e to the 0 plus b times e to the minus 0. Well, e to the 0 and e to the minus 0 are both 1, so this is just a plus b. Or in other words, b is equal to 1 minus a. So if I can find a, which I'll do from the second boundary condition, I could then use that equation to find b. Okay, our second boundary condition then tells us that y equals 5/4 when x equals the natural log of 2. So I can plug in y equals 5/4 on the left-hand side of the general solution, and x equals log 2 on the right-hand side. So the right-hand side then becomes a times e to the log 2 plus b times e to the minus log 2. Oh, well, e to the log 2, right, the e undoes the log, so that's just 2a. And similarly here, first of all, remember you can take, if you've got a number in front of the log, you can take that inside the log and make it a power. So in other words, minus log 2 is the same thing as the log of 2 to the minus 1 power, or in other words, the log of 1/2. So e to the log 1/2 is 1/2. So this is 1/2 b. Right, so 5/4 is equal to 2a plus 1/2 b. Let's substitute b equals 1 minus a that we got from the first boundary condition into here. So then we have 5/4 equals 2a plus 1/2 times the 1b 1 minus a, or in other words 2a plus 1/2 minus 1/2 a. So let's see, if I subtract that 1/2 from both sides, we get 3/4 equals 2a minus 1/2 a is 3/2 a. So a is 3/2, or 3/4 divided by 3/2. In other words, a is 1/2. Well, then b equals 1 minus a tells us what b is. So then b is 1/2. So our particular solution So our particular solution, right, we can plug our values of A and B back into our general solution here. Both A and B were equal to 1/2. So this is 1/2. I can pull the 1/2 out in front, of course. Right, 1/2 times e to the x plus e to the minus x. Or if you prefer, you can write this as the cosh of x. Right? Remember the cosh, or hyperbolic cosine, is e to the x plus e to the minus x over 2. It's just like cosine, except you leave out all the i's. Right? Okay, so that's our particular solution that not only satisfies this differential equation, but also satisfies these two boundary conditions right here. Okay? Now in this example, and again, without knowing how to solve this differential equation, you should still be able to do all of what I just showed you. Right? Sometimes your boundary conditions, like in this case, were values of y, numerical values of y at certain values of x. Sometimes they could also be numerical values of y prime at certain values of x. Right? Or even numerical values maybe of y double prime at certain values of x. Okay? And a particular example of that kind of thing that often occurs in physics is when you're looking for, let's say, a function, something that is a function of time. Right? Maybe you're describing the motion of some object. Right? Maybe it's a mass on the end of a spring that's oscillating, for example. Right? So you want to describe its position, let's call it x, maybe a one-dimensional position, as a function of time. And you might have your boundary conditions in that case might be initial conditions. In other words, at time t equals 0, x has a certain value, and maybe x prime, or x dot if you prefer, the derivative of x with respect to t, in other words, has a certain value at time t equals 0. In other words, at time t equals 0, initially, both the position and the velocity have certain specified values. Right? So that might be an example of a physics-type application where your boundary conditions might be initial conditions because you're looking for a function of time and you know what's going on at t equals 0, or initially. Okay, so anyway, that's all I'm going to say generally about ODEs right now. And again, in 473, for the first couple of weeks, we'll be spending some time on talking about different techniques depending on whether the differential equation is first order or second order, or whether it's linear, and various other kinds of issues like that. But for now, I want to go back to Laplace transforms because they can be used to solve certain types of differential equations. And so we need to see how that's done. And to do that, let's derive one more entry in that table of Laplace transforms. We already did a couple of, I think it was L1 and L2 as examples. So let's first of all notice that if we know the Laplace transform of, let's call it y of t, right? In our generic descriptions of Laplace transforms, we talked about our function little f of t, and then its Laplace transform was capital F of p. In the discussion of ordinary differential equations, your book likes to call the function y. So let's call it y instead of f, right? So y of t. Let's say that this is some function, and we know it's Laplace transform, maybe because we've actually calculated it, maybe because we've looked it up in the tables. But if we know the Laplace transform of y of t, we can find the Laplace transform of y prime of t, which stands for the derivative of y with respect to t, and the Laplace transform of y prime, in other words, a second derivative of y with respect to t. So let me show you how we can do that. Well, the Laplace transform of y, using the definition of Laplace transforms, this is the integral from 0 to infinity of y of t, times e to the minus pt dt. Okay? Okay, this is true for any function y of t. Okay? So why not replace y by y prime? Right? Y prime is some function of t also, so surely we could write the Laplace transform of y prime in a similar way. It would be the integral from 0 to infinity of y prime of t times e to the minus pt dt. Now in this integral, let's integrate this by parts. Integrating by parts, we have the integral of u dv, and this is equal to uv minus the integral of v du. Right? So let's identify our u and v. So let's let u be equal to e to the minus pt, and dv be equal to y prime dt. Right? Then this is the integral of u dv right here. Okay? So let's see. Let's then work out what du and v are. So du, the total differential of this equation. So this is minus p times e to the minus pt dt. Right? And when we take the derivative of this, we get the same exponential back again. We bring down a factor of minus p out in front, and we're differentiating with respect to t, so we have to multiply by dt. And v, well, if dv is just y prime dt, v is just y. Okay. Also, when you're integrating by parts, by the way, if your integrals are definite integrals, like this one is, this is 0 to infinity, your v du integral will also be 0 to infinity, and the uv term you'll have to evaluate at the limits, right? 0 to infinity. Okay, so let's go ahead and do this now. Okay? So, the Laplace transform of y prime, we're going to now do the integration by parts in this integral right here. So we have a uv term. So uv is y times e to the minus pt. And we have to evaluate it at the limits. And remember, it was t we were integrating with respect to. So I'm going to just say t equals 0 and t equals infinity, just to remind us what variable is being set equal to those limits. So that's the uv term. And then we have a minus the integral, again it'll be 0 to infinity, of v du. So v times du had a minus sign in front of it, so that can be used to change this back to a plus sign. So there's a p times e to the minus pt, and there's a y that comes from v and a dt. So the Laplace transform of y prime. In this first term, let's evaluate this at the limits here. If p is positive, right, e to the minus p times infinity will e to the minus infinity, which is 0. So 0 from the upper limit, and from the lower limit, when t equals 0, the exponential is equal to 1. So we just have y. But y is also a function of t, right? So it also has to be evaluated at the limit t equals 0. So in other words, y at t equals 0 will be all we get from this first term right here. I'm sorry, it'll have a minus sign in front of it because it's a lower limit. term, the p can be pulled out in front, right? We're integrating over t, not p, so p is like a constant here. And remember, y is a function of t, so I'm going to remind us that it's a function of t here. Well, this integral is just by definition the Laplace transform of y. Right? So in other words, the Laplace transform of y prime is equal to minus, I'll call it y naught, right? That means y at t equals 0. Plus p times the Laplace transform of y. So if we know the Laplace transform of y, we know what this is, in other words. Here's our equation for the Laplace transform of y prime. Okay. We can find the Laplace transform of y double prime in a similar way. Okay, so we have found that the Laplace transform of y prime is equal to p times, all right, capital Y minus y naught. Right? This is our result over there, where y naught stands for y at t equals 0, and capital Y let me remind you, capital Y is a function of p. It is the Laplace transform of little y of t. Okay, well, let's, in this expression, let y prime be replaced by y double prime, which means y will be replaced by y single prime in this expression up here. All right, so we're going to replace y single prime by y double prime. So the left-hand side will be the Laplace transform of y double prime. And so that will be equal to p times the Laplace transform, right? Capital Y was the Laplace transform of little y. But now I'm replacing y by y prime, so I have the Laplace transform of y prime. And y is being replaced by y prime, so this is now y prime naught. What I mean by this is y prime evaluated at t equals 0. Now we can substitute this same expression right here for y single prime right here. So the Laplace transform of y double prime is now p times the quantity. And now for the Laplace transform of y prime, I'm going to use this same equation again. Right, so that's substituted here, and then I still have minus y prime naught. So in other words, the Laplace transform of y double prime is equal to p squared times capital Y minus p times y naught minus y prime naught. Okay, so if we know the Laplace transform of y of t, which again is what I call capital Y. Somewhere I defined it here. Well, I guess I didn't write it that way until over there. Okay, right, this is the same thing here, though, if I write it. I can write this that way, which is the way I wrote it up over here. So in other words, capital Y is the Laplace transform of little y. Then this equation tells me the Laplace transform of y prime, and this equation tells me the Laplace transform of y double prime. So if I know the Laplace transform of y, I also know the Laplace transform of its derivatives also. Okay? In fact, I could continue the way I found the second Laplace transform of the second derivative here. I could do that again, and I could find the Laplace transform of the third derivative, or do it even again to find the Laplace transform of the fourth derivative. I could continue to find as many derivatives as I want. This is going to be useful in differential equation solving. We'll see how in a minute. But anyway, these two equations right here are also in the table of Laplace transforms at the end of Chapter 8. They are entry L35. Okay? So let's do our break now. When we come back, we'll see how we can use these to solve differential equations. We can use Laplace transforms to solve differential equations. Okay, so Laplace transforms are especially useful in solving differential equations when we want a particular solution where our boundary conditions are that certain values of both y naught and y prime naught are specified. So maybe we're looking for y as a function of time, right, where t stands for time. And maybe our boundary conditions specify the value of y at t equals 0 and the value of y prime at t equals 0. Yeah?
I don't know if I'm just being grammar nitpicky, but what does it say?
Laplace transforms are useful in solving differential equations, especially when we want a particular solution where values of y prime or y naught and y prime naught are specified. Okay? So here's our technique. Take the Laplace transform of our ordinary differential equation. In other words, take the Laplace transform of both sides of the differential equation. You can do that just like you could, multiply both sides of an equation by 2, or take the derivative of both sides, or take the integral of both sides, or take the sine of both sides, or you can do any mathematical operation you want to an equation as long as you do it to both sides. So take the Laplace transform of both sides of the equation. Okay? And when you do so, use the notation capital Y is the Laplace transform of little y, and so forth. Okay? And use table entry L35, the one we just derived, to write the Laplace transform of y prime and the Laplace transform of y double prime. Okay? The Laplace transform and any derivatives of y when you see them. Okay? When you take the Laplace transform of the differential equation, you'll probably have a y prime in there. So when you take its Laplace transform, replace it by this equation here. Whenever you see a y double prime, you're going to take its Laplace transform and replace it by this right here. And use your boundary conditions to replace y naught and y prime naught. Okay, because notice these two table entries, L35 that you've just used, contain y naught there, and also here, and y prime naught right there. Okay? If your boundary conditions specify values, numerical values of y naught and y prime naught, stick in those numerical values at this point. Okay? What you will then have is an algebraic equation for capital Y. Not a differential equation, an algebraic equation. Capital Y, remember, is a function of P. Right? Capital Y, again, is the Laplace transform of little y. Little y is a function of t, but capital Y is a function of P. Right? So capital Y is a function of P. You're going to have an algebraic equation for it. Simply solve that algebraic equation for y. Capital Y is a function of P. Then take the inverse Laplace transform of both sides. To find little y of t. Right? If you have an equation at this point, it'll say capital Y of p equals something rather, right? Some function of p. Capital Y with the Laplace transform of little y, so when you take the inverse Laplace transform, your capital Y turns back into little y. Okay? Now, of course, you're going to probably want to use the tables to do this. Right? We don't have a way of calculating an inverse Laplace transform. I told you last time that that's a very difficult thing to do. But using the tables, you can do it. Right? When you solve for capital Y of p, just scan through those tables for the columns of the capital Y's, see if you can find the capital Y you have just found in that table. If so, you can read off the little y that goes along with it, the inverse Laplace transform. Okay? Let me give you an example and show you how to do this. Okay, so our differential equation, let's say y double prime plus 4 times y prime plus 4y equals e to the minus 2t. So we want y as a function of t that satisfies this. And let's say we have boundary conditions or initial conditions y not equals 0, in other words, y equals 0 at time t equals 0, and y prime not equals 4. In other words, the value of y prime at t equals 0 is 4. Okay? Okay. So our first step is to take the Laplace transform of this differential equation. In other words, the Laplace transform of y double prime plus 4 times the Laplace transform of y prime plus 4 times the Laplace transform of y equals the Laplace transform of e to the minus 2t. Notice I've used the result we talked about earlier, that Laplace transforms are linear to do this, right? Because that allowed me to take the Laplace transform of each term separately and to pull these constants, these 4's, out in front of the Laplace transforms. Okay? I couldn't have done that if it weren't a linear operator. Okay, and then we're going to use L35. L35, which are these two equations over here, and again, that's an entry in that table, tells me the Laplace transform of y double prime equals p squared times capital Y. And remember that capital Y stands for the Laplace transform of little y. Okay? So p squared times capital Y minus p times y naught minus y naught prime. Okay? All of that is the Laplace transform of y double prime. And then I have added to that 4 times the Laplace transform of y prime. And for the Laplace transform of y prime, we're going to use the other table entry from L35, namely p times capital Y minus y naught. Okay, so that's this term, and then from this term, that's just 4 times capital Y. Again, capital Y is just shorthand notation for the Laplace transform of little y. And on the right-hand side, the Laplace transform of e to the minus 2t, we can look in the table for that. We find that it's 1 over p plus 2. That's L2 from the table. In fact, that's one of the examples we, right at the beginning of the class today, we derived that. Okay? Okay, so now let's use our initial conditions, or our boundary conditions. Our initial conditions are that y not equals 0 and y prime not equals 4. So let's plug in those values. Okay, so we've got p squared times capital Y. Y naught is 0, so this term's gone away. We have a minus 4 from this term right here. Right? Y naught prime is 4. We've got a 4p times capital Y. From this term, y naught is 0, so that term's gone. 4 times capital Y. And all this is equal to 1 over p plus 2. Okay? Or in other words, p squared times capital Y. Actually, let's write it like this. Let's take all the terms that involve capital Y, which is this one, and this one, group those together and pull the capital Y up behind. So we have p squared plus 4p plus 4 all times capital Y. There's still a minus 4 here that wasn't included in that, so minus 4 equals 1 over p plus 2. Well, p squared plus 4p plus 4, notice that's p plus 2 quantity squared. Okay? So that times capital Y, and I'm going to move the 4 over to the other side, so 1 over p plus 2, quantity plus 4. Okay. Well, as promised, we have an algebraic equation for capital Y. Right? So we want to solve for capital Y. So we solve for capital Y by dividing by the quantity p plus 2 quantity squared. We've already got a 1 over p plus 2 on the other side in the first term already, so when we divide by p plus 2 quantity squared, that'll combine with what we've already got in that term to give us a 1 over p plus 2 quantity cubed. And then the plus 4 is divided by p plus 2 quantity squared. Now, of course, we could put that over a common denominator, but it's usually easier if you don't at this point. Okay? Leave it like that. And so now we've solved for capital Y. Right? So as I said, we want to take the inverse Laplace transform of both sides to find little y. And we're going to have to use the tables to do that. So what we want to do at this point is scan those tables look in the column where the capital Y's are listed in the tables and look for something of this form. Well, you might see a couple things in the table that might be sort of suggestive. L6 in the table says that the Laplace transform of t to the power k times e to the minus at. In other words, if that's your little y, the capital Y, the Laplace transform of this is k factorial over p plus a to the k plus 1. And a and k are constants here. Okay, so in other words, we got a p plus some constant to some power in the denominator. That looks exactly like what we have in both of these terms here. Furthermore, we know that the Laplace transform operation is a linear operation. So when we take the inverse Laplace transform, it would be the inverse Laplace transform of this term plus the inverse Laplace transform of that term. Okay, so let's see, for this to work, the first term kind of looks like this, with a equals 2, right, because it's a p plus 2, and the power is the third power, so that means k would have to be equal to 2 also. The only problem is we need to have a 2 factorial, which is 2, on top, and we don't have that. But why not write this like this, right? Why not write it, multiply and divide by 2 in that first term? Pull the 1/2 out in front, and the 2 that I'm multiplying, leave it inside the square brackets, and now with that square brackets looks exactly like this with a equals 2 and k equals 2. Right? And what about the second term? Well, again, we have a p plus 2 to a power, so it looks like a is equal to 2 again, and the power is k plus 1. Well, the power is squared right there, so that means k would have to be 1. And that would mean a 1 factorial, which is just 1 on the top. So in other words, in that second term, pull the 4 out in front and write it as 1 over p plus 2 quantity squared. Right? And if you want to remind yourself that this is of that form, you could make the 1 and 2 both factorials. Right? Okay, so anything of this form, when we now take the inverse Laplace transform, all right, the inverse Laplace form of capital Y on the left-hand side is little y of t. And taking the inverse Laplace transform on the right-hand side, the 1/2 we can pull out in front. The inverse Laplace transform of the quantity in the square brackets here is this quantity right here, right, with the appropriate values of t and a plugged in. In the first term, a and k were, or I'm sorry, not a and t, a and k were both 2. So we have a t squared times an e to the minus 2t. Right? And then from the second term, we have 4 times the inverse Laplace transform of the quantity in the square brackets right there, which again looks like this with a equals 2, k equals 1. So the inverse Laplace transform will be this with a equals 2 and k equals 1. So there's a t to the first power times an e to the minus 2t. So our y as a function of t, right, is 1/2 t squared plus 4t quantity times e to the minus 2t. And if I pull out the exponential from both terms. So this is our particular solution. And it's always useful to do a double check. Whenever you solve a differential equation, you should check that the alleged solution actually solves the differential equation. This was our original differential equation. It involves both y prime and y double prime. So if y is equal to, again, 1/2 t squared e to the minus 2t plus 4t times e to the minus 2t, I just multiplied the exponential back through again because I think that's going to make the next step a little bit easier. Let's calculate what y prime and y double prime would be from this. So y prime, let's see, we're going to use the multiplication rule. We're going to have one term where we differentiate the t squared that gives us a 2t, and the 2 cancels the 1/2. So that's just a t times e to the minus 2t. There'll be another term where the t squared just comes along for the ride, and we differentiate the exponential. That gives us the same exponential back again, but brings a factor of minus 2 out in front. The 2 cancels the 1/2, but we have minus t squared e to the minus 2t now. Similarly, from this term, we have a 4 e to the minus 2t. That's where I differentiate the t, and the exponential comes along for the ride. And then I've also got a term where I differentiate the exponential, gives me the same exponential back, again, brings a factor of minus 2 out in front, that combines with the 4 to give me a minus 8t e to the minus 2t. And then let's calculate y double prime from this. So let's see. If I differentiate with respect to the t, I just get the exponential back again. If I differentiate the exponential, instead I get a minus 2t e to the minus 2t. From this next term, if I differentiate the t squared, I get a minus 2t e to the minus 2t. And if I differentiate the exponential, instead I get a plus 2t squared e to the minus 2t. From this term, I just get a minus 8 e to the minus 2t. And from this term, I get a minus 8 e to the minus 2t. And I also get a plus 16t e to the minus 2t. Well, let's simplify this a little bit. There's an e to the minus 2t in every term. Let's pull that out. Let's look for terms that don't have any powers of t in front. So there's a 1 from there, minus 8 from there, another minus 8, so it's minus 16 plus 1 is 15. I'm sorry, minus 15. And let's look at the terms that have a single factor of t. So there's minus 2t, minus 4t, plus 16t. 16 and minus 4 is plus 12t. And finally, let's look for the t squared terms. There's a 2t squared there. It looks like that's the only one. Similarly on y prime, let's kind of collect out terms. On that one, there's an e to the minus 2t, and multiplying that is 4. The minus 8t and a plus 1t is minus 7t, minus t squared. Okay. So, the original differential equation, on the left-hand side, it has a y double prime plus 4y prime plus 4y. Let's now substitute into that the expressions from over here for y, y prime, and y double prime. And we should get an identity when we do that. Okay, so y double prime, I'm going to substitute this right here. So we had an e to the minus 2t times the quantity minus 15 plus 12t plus 2t squared. What was the number there?
2t squared.
2t squared.
Just t squared?
2t
squared. Okay, and for y prime, we're going to plug in from right here. That's 4 minus 7.
I'll see if it's. We're almost done. That's just.
Am I remembering that right? It's a plus 4. And then plus 4y, right? So 4 times the quantity, and then what we got for y was 1/2 t squared plus 4t. Quantity times e to the minus 2t. So let's simplify all of that. There's an e to the minus 2t in everything, so let's just pull that out in front. So then we've got a minus 15 plus 12t plus 2t squared. That's from this. And then from this term, we have a 4 multiplied through here, so there'll be a plus 16, a minus 28t, and a minus 4t squared. And then from this term, 4 multiplied through this, so that's a plus 2t squared plus 16t.
The positive, just regular positive 2, or did I miss it? For the last term, 4 times 1/2 plus 2. Oh, t squared. I'm sorry.
Oh, yeah.
My mistake.
Sorry, I put a little curve there at the bottom of my t to make it more clear it's not a plus sign. Okay, so let's see. What do we have left? Let's look at the constant terms. We have a minus 15 there, and a plus 16 there. Those combine to give me a 1. Right? Let's look at the t terms. We've got a 12 there, minus a 28 is a, what, minus 16? Plus 16 right there. Right? So all of those cancel. And furthermore, we have a 2t squared there, plus 2t squared there is 4t squared there, and a minus 4t squared there. So those cancel also. So that's all we have, right?
Yeah.
In other words, e to the minus 2t. And that's exactly what the right-hand side of the differential equation was supposed to be, right? So we've double-checked that this is a solution, right? It came out to be the right-hand side as expected. So this is a double check that our solution works. And we can also check the boundary conditions, right? This kind of check is always a good idea because if we've screwed up somewhere along the way, we'll catch it at this point, okay? It won't work out. Okay, so our boundary conditions were that y naught equals 0 and y naught prime equals 4. So y, right, our solution for y, which was down here, 1/2 t squared plus 4t, all times e to the minus 2t. If we plug in t equals 0, right, that'll be 0, that'll be 0, e to the 0 is 1, but this thing multiplying it is 0. So if we plug in t equals 0, we verify that y naught is 0 as expected. Right? That was one of our boundary conditions. We can also verify that our other boundary condition works. Our other boundary condition was on y prime. The expression we got for y prime right here, 4 minus 17 minus t squared. All times e to the minus 2t. If we plug t equals 0 into that to get y naught prime, well, e to the 0 is 1 out here, so just plugging in right here makes that 0 and that 0, so we get a 4 from that. Again, as expected, right? So this function right here satisfies both our differential equation and our two boundary conditions, right? And we double check them both. So this is how you can do this, this Laplace transform solution. So again, this is an especially useful technique. It's mostly for first and second order equations. So the example we did there was a second order equation. Again, especially where we want a particular solution where certain values of y naught and y prime naught are specified, because again, the L35 expression that we use to substitute for the Laplace transform of y prime and the Laplace transform of y double prime involves both y naught and y prime naught. So we have particular values, we again plug those in, okay? So this is useful in a lot of differential equations that again arise in physics and engineering applications. For example, if you're doing circuit analysis, I know that's an application that a lot of you computer engineers and applied physicists might be interested in. When you are analyzing an electric circuit, you can use Kirchhoff's laws, in particular Kirchhoff's loop rule, which hopefully you remember from Physics 222. It means that you go around any closed loop in the circuit, and remember you add up all the voltage gains and losses, and they have to add to 0 for the complete loop. If you've got a resistor, of course, you can put a voltage drop equal to the current times the resistance. Similarly for other elements, right? If you have a capacitor, you can put a voltage difference of Q over C, right? The voltage difference across the two plates of a capacitor is the charge Q divided by the capacitance C. Similarly for an inductor, there's a voltage difference which is the inductance times the derivative of the current with respect to time. And remember, the current is the derivative of the charge with respect to time. When you substitute all of those things in, your loop rule equation is going to become a second order differential equation for Q as a function of t, where Q is the charge on your capacitor plates as a function of time. Okay, if you are given an initial condition, like that Q has a certain value at time t equals 0, and that I, the current, which is, again, the derivative of Q with respect to t, has a certain value at time t equals 0. Then those are your initial conditions, right? The charge as a function of time is now this function y that you're solving for in the generic mathematical notation that we used here. And your initial conditions, right, you have values of y naught and y prime naught that you can then plug in, and then you can do a Laplace transform solution of that differential equation in exactly the same way we just did for this example. Okay, so you can do any of these loop rule type equations that arise in circuit analysis this way. Okay, so again, that's I think a useful technique for all you computer engineers and applied physics types. Okay, so we are out of time today. We'll talk about something else related to Laplace transform, something called a convolution next time. Okay?